So folks, in this section we want to look at what are called autonomous ODEs, and we'll look at equilibrium solutions and the stability of those solutions as we study these. So what is an autonomous ODE? Well, an autonomous, you think of the word autonomous as you've used it in the real world. Autonomous in this sense means that the ODE does not depend on the independent variable. So for example, in this ODE right here, the independent variable is x. And notice that the value of the derivative, dy dx, does not depend on that independent variable x. So this is an autonomous ODE. Well, this ODE, here again, the independent variable is implied to be x. It does depend on the values that x takes on in order to compute the value of the derivative. So this one is not autonomous. Another way to say that is that autonomous ODE could be written as, let's use it as, say, dy dx is equal to just some function of y. So notice that f, whatever f is, some combination of operations, it depends only on the dependent variable y and not upon the independent variable x. So again, if we had, maybe we wrote our differential equation this way. Here x is implied to be the dependent variable, t is the independent variable, so this would be autonomous if we could write it as f of x. Or if we were using, say, dy dt, this is autonomous if it could be again written as f of y. So the key thing is the function that we're able to, when we isolate the derivative, putting it in normal form, if that function depends only on the dependent variable, then this is an autonomous ODE. So absolutely essential for understanding the solutions of autonomous ODEs are to look at what we call critical point solutions. So a critical point of an autonomous first order ODE is some real valued constant so that when you plug it in place of y into the function that's on that right hand side there, because it's autonomous, we know that that is just a function of y. If we plug in that value c so that it outputs a 0, then we're going to call that c value a critical point. By the way, critical points are also called stationary points, or they're called equilibrium points. Put another way, a critical point is an equilibrium solution. I'm sorry, I wanted, that's true, but I want to say a constant solution to the ODE. How come? Well, because if I say y equals c solves the ODE, and we know, since it's a critical point, that f of c is equal to 0, let's just check that. If you take the derivative of what your proposed solution is, the derivative is 0. And so into dy dt equals f of y, we're going to, if we plug in the solution c into this, well, the y prime would be 0 on the left-hand side, and on the right-hand side we'd have f of c, but we just said that that is 0, and so we end up with the identity 0 equals 0. So constant solutions stem from, for autonomous ODEs, those critical points. So finding those critical point solutions is absolutely essential, and what's nice is it's actually not too hard to do so. So let's go ahead and look at an example. In number 18 here, we have an autonomous ODE. Let's just double check that, and my screen's freezing on me. There we go. We have an autonomous ODE. Let's just check that. Notice that this is written in that differential or that normal form. We've got the derivative of x is equal to, and then the function on the right-hand side depends only on x. What I'm saying here is you could imagine this as some function just in terms of x, and it does not depend on the independent variable t. So the ODE is autonomous. Now, if you were to go to try to find an explicit solution to this, let's actually do that work. This is an example of a separable ODE, so no problem, we could do that. Doing that separation of variables technique, we'd have dx over x times x minus 2 times x minus 5 is equal to negative 1 dt. So I multiplied the differential t over the other side, and I divided the function of x over, I dropped off the negative, but I divided the rest of the function of x over onto the left-hand side. Notice that this is something that you could break up using partial fraction decomposition. And so breaking up and integrating with respect to the given variables, it turns out, and you could check this, this comes out to be 1/10 over x plus, oops, that's minus, so put plus negative 1/6 over x minus 2, and then plus 1/15 all over x minus 5, and you could check that. Differential x is equal to the integral of -1 differential t, and you could continue to work to solve this, and I'll just put could continue, and so that should look somewhat familiar. It should look like something we've done before, so you could continue that. But a better way to analyze this solution is to look at the critical points. Let's look at the critical points. Remember, what we're calling the critical points are the constant solutions y equals c so that f of c equals 0. That is, we're looking for the zeros of the function on the right-hand side there. And I should be a little more careful here, folks. I'm sorry I used y. That's because I was using y earlier. I should have used, in this case, our dependent variable is x. And so I should be using x equals c. So notice that the three constant solutions are x of t equals 0, x of t equals 2, and x of t equals 5. Those are the three constant solutions to this ODE. And we're going to talk more about this in class, but I want to point out something. We could make what's called a one-dimensional phase portrait here. And what I'm going to do is I'm going to draw my dependent axis, and that's a little bit weird to put the dependent axis this way. Some books will actually go ahead and orient it this way when they draw these diagrams, but I'm going to follow our author's example. And then we're going to put those equilibrium solutions on here. So here's the equilibrium solution at x equals 0. Here's the equilibrium solution at x equals 2. And here's the equilibrium solution at x equals 5. And so again, rather than focusing on finding the explicit solution to this, which we could do by continuing to solve this equation right here, we're looking at these solutions more qualitatively. And what I've done here is I've labeled all of the critical solutions on here, or the critical points on here, the stability points or the equilibrium solutions. These are the solutions where if you plug in the function x of t equals 2, it is a solution to the differential equation. It's a very boring solution because that function never changes. So what I'd like to do now is similar to techniques you've seen before. Let's go ahead and classify these solutions by taking test points from within this interval. So I'm going to pick some test points here within these intervals. So let's pick x equals -1. Let's pick x equals 1. Let's pick x equals 3, and we'll pick x equals 6. And I'm going to plug all of these into the original ODE, and I'm going to simply examine the sign on dx dt. I'm going to look at the sign on the derivative here when I plug in these constant solutions. So if I were to plug in a -1, let's see what we get. So if I plug in a -1, that first factor would be minus a -1, that's a positive. This would be -1 minus 2, so that's a negative. -1 minus 5, that's a negative. So I've got a positive times a negative times a negative. So the result is anything I pick here will be positive. What does that mean? That means that the y values will be increasing. This is a little bit maybe convoluted if you're not really thinking about it. The y values will be increasing, meaning we would expect the y values to be moving up towards 0. Similarly, if we picked 1 and we plugged it in, notice that this first factor would be negative, the second factor would be negative, the third factor would be negative, the product of three negatives is again a negative. And so if I were to take the state where x is equal to 1, as time progressed, we would expect this thing to be decreasing because dx dt is negative there. Okay? Likewise, if we were to plug in 3, we would have a positive, so that would be increasing. And if we were to plug in 6, notice that we would have a negative, so we would be decreasing here. Okay? So folks, we're going to go through these four phase portraits in more detail in class, but I wanted to at least give you the exposure to them. Okay? But look at these different equilibrium solutions then. Notice that if I take the equilibrium solution 0 and I perturb it just a little bit, like I tried the solution x is equal to 0.1 or x is equal to 0.5, that my solutions will continue to decrease back to 0. Same thing if I were to perturb it a little bit the other way, we would decrease to 0. So we're going to call this a stable equilibrium solution. Unlike x equals 2 here, which is called an unstable equilibrium solution. Meaning, if my differential equation is in the state where the current dependent variable is 2, yeah, this thing will never change. But if it were just a little bit more than 2 or a little bit less than 2, it would tend away from there, because if it were just to the right of 2, we would expect it to continue increasing away from 2. And if it were just a little bit less than 2, like 1 or 1.9 or something like that, we would expect the value, the value is negative, so we would expect the solution to begin to decrease away from 2. So that's what we mean by an unstable equilibrium solution. I imagine, and a lot of other math people do too, that if you had, say, a scenario like this where you had a ball sitting right here, that ball is not moving because it's sitting in an equilibrium solution. If you were to perturb it one way or the other, it would still eventually kind of return back to where it was. But if you had a ball sitting up here, yeah, if you've set it just on top of the hill just right, it won't move. But if you perturb it just a little bit, it moves away from that solution. And this would be our example of a stable equilibrium solution, and this is unstable. Okay, folks, we're going to pick this up in one last video here, because this one's getting a little bit long, and we will actually do the 2D phase portrait for this solution, which will get us ready for Wednesday's class. Thank you very much. Let me know if you have any questions.